We've made some effort to define concentration in the solution. Now it's time to talk about another type of compound, one that does not dissolve as readily in water. Our learning goals for this are going to be to define the characteristics of electrolyte solutions and then how to use tabulated information so that we can predict when compounds are going to be soluble or insoluble. So let's start by considering what exactly happens when we dissolve salt in water. Okay, it's something that we've probably all done in the kitchen at one time or another, but what's actually happening down at the atomic level? Well, when that sodium chloride hits the water, it ends up being broken up into its separate ions, its sodium ion and its chloride ion, and those ions are individually solvated by water molecules. Now, what do I mean by that? Okay, the way water holds onto a solute is it surrounds the particles of solute with water molecules. And so what happens in this case is the sodium ions are surrounded by water molecules and the chloride ions are surrounded by water molecules, but they're surrounded separately. So they're basically separated from one another, and each one of them is basically gang-tackled by a bunch of water molecules. This is the prototype for an electrolyte solution. It's basically whenever there's an ionic compound that dissolves and dissociates into its component ions when it dissolves, it forms an electrolyte solution. One of the properties, interesting properties of electrolyte solutions is that they often can conduct electricity, and you can probably find some videos on YouTube that will show you this very fact. But for our purposes, what we really care about is that it splits into its ions, so it's now present in the solution as charged ions. Now, there can also be reactions that take place in electrolyte solutions. We've actually seen an example of that in an earlier video. In fact, it's this particular reaction of a chloride ion reacting with methyl bromide to form methyl chloride and bromide ion. But one thing I want to point out in this particular layout of this reaction, where we're showing all of the various species that would be present in the water, is that we've got sodium on the left side and we've got sodium on the right side. It didn't change. Nothing happened to it. Well, we have a special name for this. We call it a spectator ion. All right, since it doesn't take part in the reaction itself, in fact, we don't always write it down. We sometimes will leave out spectator ions and simply write a net ionic equation, which would be written with everything else except for the sodium ions. All right, I've included them here so that we can emphasize the result that they do not participate in the reaction. They're simply there for the show. All right, let's talk about insoluble compounds. So there are some ionic compounds that do not readily dissolve at all in water, and let's talk about them and how we can figure out which ones they are. Now, I'm going to focus on the left-hand side of this table to begin with, and then we'll look at the right-hand side. Okay, the left-hand side shows us the things that pretty much are soluble. Okay, the first two rows, in fact, are completely soluble. Any compound, any ionic compound that has lithium, sodium, potassium, or ammonium as its positive ion pretty much is soluble. Any ionic compound that has nitrate or acetate as its negative ion, they are pretty much soluble, with no exceptions. All right, now we also have some of the halides, chloride, bromide, and iodide. Most of them are soluble. There are only 3 exceptions you need to worry about. Those are silver, mercury, and lead. All right, but anything else that's got a chloride there, it's probably going to dissolve in water. Sulfates also primarily dissolve in water. There are some exceptions, though. The second column of the periodic table has many of them. Calcium, strontium, and barium do not dissolve. Those sulfates do not dissolve. Also, lead and silver do not dissolve. So what you would look for is when you're considering whether a compound will dissolve in water, if it's got one of these ions in it, look to see if the other ion is one of the exceptions. If not, then it's soluble in water. Okay, now let's look at the ones that are principally insoluble. And there's only 4 ions that we're going to worry about here: hydroxide, sulfide, carbonate, and phosphate. Okay, for hydroxide and sulfide, again, lithium, potassium, sodium, and ammonium, they're all soluble, so they are exceptions to this insolubility. Now, we also have some other ions, calcium, strontium, and barium, with the sulfide, they are soluble. Okay, so they are exceptions for that. For the hydroxide, they are slightly soluble. Okay, but all other sulfides, all other hydroxides would generally be insoluble. For carbonate and phosphate, Again, the only ones that are exceptions to this are the ones in the first row, first column of the periodic table: lithium, sodium, potassium, and then ammonium. All right, so once we have all of this down, we can now ask questions like, when we have a couple of compounds, are they soluble in water or not? So let's do some of those just for fun. So let's consider sodium sulfide and lead sulfide. Are they soluble in water? You could pause here and try it yourself, or you can stay with me and listen to the solution. Well, sodium, everything sodium is soluble. So if you see sodium on it, doesn't matter if it's sulfide or something else, it's soluble in water. What about lead sulfide? Well, sulfide is one of the insoluble ions, and lead is not listed as an exception. So that means lead sulfide indeed would be insoluble. So lead sulfide is not soluble. Let's try another one. I got calcium sulfate and potassium sulfate. Well, once again, potassium is one of those things that doesn't matter what it's bonded to, it is pretty much soluble. So the potassium sulfate, we can pretty much count on it dissolving in water. What about calcium sulfate? Well, sulfate is listed under the soluble ions, but one of its exceptions is calcium. So in fact, calcium sulfate is not a soluble compound in water in this case. Now, once we have a handle on what's soluble and what's not, we can begin to understand precipitation reactions and make predictions about it. So whenever there's an insoluble compound and it's a product of a mixture of two solutions, it will appear as a solid. It will precipitate out of the solution. So let's look at a good example. Let's suppose we took a solution of sodium chloride and a solution of silver nitrate and we mixed them together. Well, first of all, they are both electrolytes, so they would form strong electrolyte solutions. We'd have sodium ions, chloride ions, silver ions, and nitrate ions all wandering around in there. So now the idea is we want to analyze this and determine if any of the combinations that are possible result in an insoluble compound. So as we do our analysis, okay, we know that sodium forms a soluble compound with just anything. So sodium chloride and sodium nitrate, absolutely soluble. Nitrates are all soluble, so silver nitrate, we dissolved it in the first place to make the solution. So all of these are going to be soluble. But silver chloride is one of those that is not soluble, and we mentioned that on the previous slide. So in fact, what will happen is that when we mix these things together, the chloride ions and the silver ions will find one another. They will form an insoluble component in that solution. They will form a precipitate. So I hope this has given you some clues for how to analyze these things. You need to be able to read that table. You don't have to memorize the table, but you need to be able to read it to determine which things are going to be soluble and which things are not.